Okay, so let's start the session. So, in this week, that is the week 12th lecture, what we have seen the a demonstration of one of the hydrological model, and then some of the miscellaneous thing that we have left in the whole course, and then we have done one kind of summary of what all we have done, and then the questions, some numerical and some objective questions on all the topics of the watershed hydrology. Okay, so with that, let me switch off the videos. Yeah. Yeah. So hello everyone. I'm Balram Shah. I'm the PMRF TA for this course, that is Watershed Hydrology, by Dr. Rajendra Singh in the Department of Food and Agricultural Engineering in IIT Kharagpur. I'm a PhD scholar at Interdisciplinary Center for Water Research at ISC Bangalore. So in this session today, we will be discussing about the week 12 lectures that I hope you guys have gone through it. So in this lectures, mostly it will be like the model demonstration was there, one of the hydrological model. So in one of the weeks, we have discussed in detail about the watershed modeling or hydrological modeling, and then what all, how we do the project setup or the model setup, then the calibration, validation, and so on. Right. So before moving on to the questions, let me switch off the sharing from here. Give me a minute. I hope you guys can see the screen. So I'll not be showing you the demonstration of model because anyway we have seen that in lecture. You can just go through the lecture videos and try to at least do one model, if not HPV or some other model, you should try so that you get the full grasp of what kind of model, how the model works, and so on. Right. So start. So firstly, we have seen one of the ecological model demonstration. So before this, we have seen several, while discussing the hydrological models, we have seen there are several models like HPV, then SWAT, right, then ABCD model, water balance, water budget model, and so on. There are several hydrological models that we have seen. Okay, several. We have seen the classification of the models also, like what are conceptual models, then what are empirical models, right? Then we have also seen distributed, semi-distributed, lumped model, right? Yeah. So in this lecture, we have only seen the demonstration of HPV, right? Um, so this one is mostly HPV. HPV is widely used for runoff simulation. So what I feel, why this HBV is or where this HBV model is used, because when we were discussing about the hydrological models, remember we said that any models should be used with caution, like where we are using for what application. For that we need to know that which kind of model we are using, because not all the models are perfect, right? So every model has their own limitation, has their own advantages. So based on that we should use that model in that application, right? So HPV model is mostly used in runoff simulation in those areas where snow is prominent, kind of. So let's say if some glaciated catchments are there where we have snow and snow cover and so on. So in that case, I feel that HBV is most useful. Okay. So HBV is a conceptual model, right? And it also comes in the category of, like, we can use this model as a fully distributed or a semi-distributed model. Okay, so what we do, we divide the whole catchment into small catchments, or let's say if you go smaller than that, let's say you go for hydrological response in unit. So we have discussed about the hydrological response unit also. So let's say based on the okay, uh, sub catchments or sub basins, whatever you say, and then based on maybe land use, land cover. So in that comes the vegetation zone also, vegetation zones. Then based on depth, that is elevation, based on soil classification, and so on. Based on several catchment properties, what we can do, we can classify or we can reduce the size also. In that case, it will become it will work as a fully distributed model, right? And what are the inputs that we need in this? Meteorological inputs are precipitation. And remember, when we were talking about the precipitation, precipitation is not only the rainfall that we receive in the form of liquid water, but also the snow or ice that we are receiving, right? So precipitation will be for all the rainfall, snowfall, and so on, clays, all those we have studied in precipitation. Then temperature can be it will be maximum and minimum temperature, then mean temperature or mean monthly temperature. So from there we can also calculate, or if we have, we can use the potential evapotranspiration. the methods and all we have discussed before, right? So with all these inputs, we can uh, get our simulated runoff, right? Okay, so before moving on to the output, we'll see the model structure. About the HPV model structure. So in HPV model, it consists of four models. I mean four modules. So these are the sub-models, right? Sub-models. Sub-models are snow module. Modules. So first one is the snow module. Second one is the, I'll discuss all this one by one. Second is the soil module. Third is the response function. And fourth is the routing routine. Right? So coming to the first one, that is snow module. In snow module, what we consider? We consider as we talked that we need precipitation data, temperature data, and then other land use and characteristics data also in the form of parameters and all. Right. So in this snow module, what we see is snow. Okay, so in this snow module, it is basically doing snow melt modeling. So how does snow melt is happening at what temperature? Sorry. Snow melt module, right? So in this snow module, what it basically does, it basically does the modeling of the snow melt. So let's say how the precipitation is coming, and based on that, let's say because of the temperature, how the snow is melting, and why we are doing this snow melt modeling, because this snow melt will give its input to the runoff, right? Because let's say Ganga catchment or Ganga basin. In the Ganga basin, it receives water the whole year, all the times in the year. So it's not like rainfall is happening throughout the year, but in the monsoon season it is receiving rainfall. But in the remaining time of the years, how it is getting the water? It is getting water from the glaciers, right? Because of the snow melt and so on. So like that, for that we need the snow melt modeling, and in this snow module, it considers the traditional degree day approach. Okay, so what is this degree day approach? So as per this, I'll write degree day as DD. As per this degree day approach, let's say if the temperature is less than the threshold temperature, I'll write T. So this is the threshold temperature. So let's say here we are what we are calling degree day, right? So if the temperature of the day is less than that of the threshold temperature, let's say based on whatever region we are in. So if the temperature is less than that of the threshold temperature, what do you think what will happen there? So let's say if melting is happening or freezing is happening. If freezing happens when that uh, the temperature goes below a certain temperature, right? So like that, if the temperature of the day is less than that of the threshold temperature, it will lead to a accumulation of the snow, right? Because freezing will happen kind of. So accumulation of snow, the accumulation of precipitation will be happening. Okay, of precipitation will be happening in the form of snow, as snow. Okay, so this one is the first. Now second is, if the temperature is greater than the threshold temperature, then what will happen? Then melting will happen, right? melt of snow. Okay, and for this we use a factor. So how do you calculate snow melt? This is snow melt. Let's say snow melt will be equals to Cf max into T minus T naught, where T naught, as I said, is the threshold temperature. Okay, and this is one of the coefficient. This is the degree day coefficient or degree day factor, whatever you say. Okay, and the unit is in millimeter per centigrade per day. Okay, now the unit for this is the remaining portion. Unit for this is what? Unit for this will be in degrees Celsius. So what will be the unit for this? Unit for this will be what? See, millimeter per degree Celsius per day. So the unit of snow melt will be millimeter per day, right? So this formula we use for T greater than T naught. Okay, if T is less than T naught, then as I said, snow melt will freeze again. Okay, then let's say I'll write refreezing snow melt will be equal to CFR into CF max into T minus T naught. Or because here T naught is greater, so it would be T naught minus T, sorry. T naught minus T. Okay, and here this is the refreezing constant. Okay, so here you see, here it is accumulation of precipitation as snow. So precipitation is coming as snow, or snow is coming as precipitation, right? This is when the threshold temperature of that day is less than that of the temperature of that day is less than that of the threshold temperature. Now what happens? Let's say temperature increases for the next day. Now if it increases the threshold temperature, then melting of snow happens. Now again, let's say after 5 days, the temperature of that day decreases below the threshold temperature. Then what will happen? Again, refreezing will start, and hence becomes the refreezing snow melt. And for that, we have a refreezing constant or refreezing factor. So all the precipitation that is simulated to be snow should be multiplied by a correction factor, that is SFCF. Okay. So topography is usually counted for by the area elevation zones and temperature and precipitation lapse rate. Okay, so this one was the first, that is snow module. Okay, next is the soil module. Sorry. Okay. Next we'll move to the second module, that is soil module, or let's say soil moisture routine. Okay, so in this it is basically mostly based on the soil moisture accounting factor. So let's say how much soil moisture is accounting to the runoff and so on. So soil moisture storage will be considered as the key variable, which will vary from, so let's say soil moisture, how it will vary. If you would have studied any of the irrigation subjects also, you will know that soil moisture storage, the minimum value obviously it will be 0, right, and the maximum value will be FC. What is FC? FC is the field capacity, maximum soil moisture that one field can have. Let's say if you are considering in a meter cube or in millimeter, right? So the relation of this soil moisture to FC ratio, FC will varies from 0 to 1. So let's say if you are taking one ratio, that is soil moisture storage or soil moisture to this, so it will vary from 0 to 1. Okay, and this one is considered as the index value. Okay, and it will denote that how wet it is. So let's say 0. 0 means what? See, the soil moisture storage is if soil moisture storage is 0, then only this ratio or this index will be 0, right? This means what? This is a dry soil. And whereas if it is 1, this means that soil moisture has reached the field capacity and hence it will be a wet soil. Correct? Right? So it will determine that how much water will become recharged and eventually run off and how much remains in the soil. Okay, and this soil moisture will be what will happen, how it will go out, it will go by or it will get depleted by evapotranspiration, right? So generally we use the recharge to LP ratio, that is the soil moisture value above which this actual evapotranspiration reaches the potential evapotranspiration. Okay, so we have several empirical formulas for this getting the soil moisture or the evapotranspiration, right? So this one was the soil module. Next we have response routine. What is response routine? So in this we simply consider that the model or the response behaves as a simple linear reservoir, right? So this means what? So let's say if we consider one bucket kind of thing and the water is something like this. So precipitation will happen like this. There will be, this will be the storage change or the storage, and then it will come out as runoff, right? And this linear in linear reservoir model, in the very beginning we have considered that how we write the linear reservoir model as K into S, where S is the storage and Q is the runoff, correct? So we consider two buckets kind of thing, and then based on the bucket model, we get the response of the discharge or recharge. Let's say. I'm not going deep into the like how we consider. You might have seen that in the lectures, right? And last but not the least is the routing routine or routing approach, whatever you can say, right? So in this routing routine, you remember routing? We have studied about the hydrological routing, hydraulic routing, and so on, right? So what we consider here, we consider a transformation function so that we can route the information that we have for one location, right? So the generated runoff, let's say of a one-time step, is distributed on the following days using one free parameter, okay, which will determine the base in an equilateral triangular weighing function, right? So these are the main modules of the HBV model. Okay, so now while doing this, for each of this module that you can see, we go for we consider some model parameters, right? So we have discussed about the model parameters and all. I'm not going. So it can be for each of the modules and so on. So each of the characteristics or each of the parameters denotes some of the characteristics. So let's say temperature. Okay, threshold temperature. Threshold temperature is what? Threshold temperature is one of the meteorological parameters, right? Based on that, we can understand that if it is less than, if the temperature will be less than threshold temperature, then this will happen. If the temperature is more than the threshold temperature, then this will happen. So this is one of the meteorological parameters that will be used in this model. Similar to that, there will be several watershed characteristics also, right? So let's say there can be water holding capacity, like how much water it can hold the catchment, right? So this is one of the catchment property, right? Other than that, there will be several other storage, like storage coefficient, and then other watershed characteristics or other meteorological parameters and so on. So whenever we are doing hydrological modeling using some model, this parameter will help you set up the model, right? So how much values or the range of values in which the your model should be will be done while doing the calibration validation. So after the with this model parameters we are done with the model setup, what we have to do, we have to do the calibration and validation, right? So we have studied about the calibration and validation in the logical modeling class, right? So mostly this calibration will be done in trial and error technique. We or if you go for automatic one, it will use the Monte Carlo simulations. So there are different criteria which can be used to assess the fit of the simulated runoff. We have seen several performance metrics, right? Performance metrics like RMSE, R square, NSC, KGE, right? Other than that, we can, like, let's say if you plot the simulated runoff and the observed runoff that you have, if you can just plot, you can just visually also see, okay, this much difference we have. This means the model is not that not taking the runoff. So let's say this is the runoff, this is the time monthly runoff, let's say, and the runoff is something like this, let's say. Okay, so this is the observed runoff, let's say. Okay, and you have some the simulated runoff something like this. See, so here the blue one represent the simulated runoff by the model, right? Now you can see, if you see properly in visually, just see, if you don't need any performance metrics, just to understand on the like visually also you can say whether your model is very good or not very good, something like that, right? So let's say if you have this observed runoff and simulated runoff, okay, from here you can see the simulated runoff is following similar pattern of that of the observed runoff. So you can see the seasonality that observed runoff is having. The simulated runoff is also having the similar seasonality. But here you can see that the peaks that are there in the observed one, that is not well taken care by the model, right? So from here you can understand whether the uh, simulated runoff is can be used or not, right? So whether you have to change the parameter, something like that. Okay, so by this also, by visual inspection also, you can assess whether the simulated runoff is good enough or whether the set model is good enough or not. Other than that, you can see the accumulated difference and so on. Okay. So like that, after calibration, if you see, okay, the my now my performance matrix is performing well when we are calibrating. What you do, you use the remaining runoff value for the validation, right? Let's say generally people use 70%, 30%, 70% for calibration, 30% for validation, something like that, right? And then you check if the in the validation also you are getting good performance metrics. You consider that that model will uh, be taken considered for your further analysis. Okay, so so mostly this is for the HPV model, but the whole thing that we have seen can be for other models also. So the what are the applications of hydrological model or, of this HPV? It can be used. So let's say after you validate the runoff, you can use it to generate or to extend the runoff data series. So what you can do, you can do future forecasting or prediction of the runoff for, let's say, some years. Okay, or you can fill the data that you have. So let's say if there are data gaps, you can fill those also. So you can use for water balance studies or climate change studies and so on, right? And that is for forecasting you can use. For flood what else you can use. Right? Computing, design flow, something like that. There are several applications we have seen this earlier, right? Okay, so we'll do some questions on this HPV hydrological model and then again we'll come back. Okay. So the first question is HBV hydrological model can be used as anyone? We have just seen this. So we have seen that HBV hydrological model can be used as both fully distributed or semi-distributed model. Right? So the correct answer is D. Next question is the snow routine in the HBV hydrological model is based on you know so soil moisture accounting approach. This we have seen. This is for the soil routine or the soil module. Right? The triangular weighing approach we have seen. This is the sorry routing routine. Or routing approach what we have seen. The bucket model we have seen. This is in the response function. And this dignity approach is considered in the snow module or the snow routine. Right? So the correct answer will be degree day approach. And we have seen that degree day approach considers that if the temperature is greater than the threshold temperature or the temperature is less than the threshold temperature, based on this, it considers that how much will be the snow melt or whether there will be snow melt or stray freezing and so on. So the correct answer will be B, that is degree day approach. Okay, so the next question is the catchment in the HBV hydrological model can be divided into different elevation zones, with each zone having which kind of corrections? Okay, so while doing the model setup, one of the one of the step that we do is the catchment setting. Okay, so in catchment setting, what we do in catchment or what catchment setting helps in, it offers the option to input various parameters such as catchment properties, area, elevation. Okay, so in this you will get area, catchment area, or elevation, or properties of some properties of the catchment. These things you can input. Okay, and these catchments are divided into different elevation zones, right? So for each of the zone, we do both the precipitation correction and temperature correction. Okay. So for each zone, precipitation will be corrected according to its increase with the elevation. So let's say if the elevation is increasing, then how precipitation will change above the sea level. So usually we consider 10 to 20% per 100 mm, right? 10 to 20% for 100, sorry, per 100 meter. Okay, And for temperature, for each like zone, temperature will be corrected according to its increasing with elevation again above the sea level. Usually minus 0.02, sorry, minus 0.6 degrees Celsius will be considered per 100 meter. Okay, and the parameter that we use for this is PCALD in the HPV model. Okay, remember I am talking only about the HPV model here. Okay, for other the name can be different. So in this, the correct answer will be option A and option B. Okay, so the correct answer will be C. That is both A and B. Okay. Okay. Any questions here? So the correct answer is C. Okay. So before moving on to the next question, we will just go through some things again. So after this, we have seen about the land capability classification, right? So what do you mean by land capability? Anyone? So land capability means what? So land capability is the capacity of the of any land surface which supports various uses such as natural plant growth, or it might be wildlife habitat, then artificial crop cultivation, human habitation. So for various use, if the land surface is capable, we call that as the land capability. Okay, so yeah, I'll write it here. Capacity of a land surface to support various uses such as it can be natural plant growth, wildlife, or let's say human, also human habitat, habitation, etc. It can be like crop cultivation and so on. So generally we determine this using several factors such as slope, like how is the slope. Okay, so let's say if you consider that if it is a high slope, okay, or it is a steep slope, not high slope. If it is a steep slope, then what will happen? Most of the trees will be different, right? Based on the slope, how whether it is capable of some use. Okay, for now let us consider natural plant growth. So if you consider plant growth of one kind of plant in a steep slope, it is not possible. For some of the plant only it can sustain. So this land capability is determined based on slope, based on the soil type, based on the depth, then based on the erosion control or erosion conditions, and so on. Based on several factors, we determine this land capability classification. And why do we do this? Why do we need this land capability classification? So we do this to understand whether like any piece of land and is defined for some of the conservation and possible treatments. So conservation problems and possible treatments. So let's say if we will classify the land. So let's say if land is very good or land is very bad. If land is very bad, what kind of conservation problems it have? So after knowing that, we can have some possible treatments for those kind of land classes, right? So for that, we need to have this land capability classification. Okay. So there are total 8 classes. Sorry. So there are total 8 classes. Okay. That also is divided into two. First 4 classes, these are suitable for cultivation, and the second 4 classes. So the first 4 classes, it's like one, two, in the Roman numbers 1, 2, 3, 4, and the second 4 classes are like Roman number 5, 6, 7, 8. Okay. So if it is in this, it means it is unsuitable for cultivation. Okay. Just to note here that it is suitable for cultivation and unsuitable for cultivation. That doesn't mean this soil is not considered in anything. That is useful for, but for some habitation. We'll see that. Okay. So coming to the classes which are suitable for cultivation, generally the first slope is within 1%. The slope will be within 1%, and hence, let's say if there is no slope or like minimal slope, this means what? It will be a very good arable land with no specific difficulty in farming. So if it is a flat land with no slope, then the farming can be easily done, and hence it will be considered as first class land capability class. Okay, so in second class, that is class 2, the slope will be in the range of 1 to 3%, and hence the good cultivation land it will have, which needs protection from erosion or floods. Okay, the third class, that is class 3, it is in the slope is ranging between 3 to 5%, and as the slope is increasing, this means what? That cultivation will be moderately good, where special attention has to be paid to erosion control. Okay, in the fourth class, that is in the class 4, the slope will be between 5 to 8%, and it will be fairly good land suited for occasional and limited cultivation. Okay, and needs intensive erosion control. So in all these three, we need the erosion control, and the erosion control um, stiffness will be increasing as we move towards the slopy kind of land. Okay, and in the second 4 classes, that is 5, 6, 7, 8, as we are moving, so as we are moving to 1 to 8, let's say, what we can see, that slope is increasing in this direction, right? So slope 5 will be in the range of 8 to 12%, then 6 will be ranging to 18%, 7 will be ranging to 25%, and if it is more than 25%, it is the 8th classification, steepest slope. Okay, this steepest slope, if you say, I said it is unsuitable for cultivation, but it is suitable widely, mostly for wildlife. Okay, the seventh one will be suited for fairly well suited for grazing or forestry with little carrying capacity of livestock. Okay, 6 will be well suited for grazing and forestry, but not for cultivation of crops. And the fifth will be very well suited for grazing and forestry, but not for cultivation of crops. Okay, so these are the land capability classification. There are several subclasses also, like subclasses E means there is a risk of erosion or past erosion damage has been there. The W means wetness damage or overflow. S means soil root zone limitation. C means climatic limitation. So it will be like 1C. So 1C means what? 1 means class 1 capability classification with C means what? That there is climatic limitations. Okay, so like that there will be land capability classification. Okay, next will be land suitability classification. So it's kind of similar, but let's see. Land suitability classification. Okay, so land suitability classification, it will show you the fitness of given type of land for some use, for a defined use. Okay, in this also based on several factors, it will be either suitable land or not suitable land. Okay, it will be like S1, S2, S3. This will S1 means highly suitable, and S3 means marginally suitable. Okay, so S is suitable and N is unsuitable or non-suitable. Okay, again it has several subclasses and so on. Okay, let's see some questions on this. Okay. So the next question is, which of the following best describes the objectives of land capability classification? So we have seen that why do we do the land capability classification? We mostly do so to understand the conservation problem or give some possible treatments to it, right? So the options are to determine the market value of land, to access the agricultural potential and limitations of land, to identify the geological composition of land, and to evaluate the aesthetic appeal of the land. So obviously, the correct answer will be B. That is to assess the agricultural potential and limitations of land. Right. Next question is, which class in the land capability classification typically represents land with the highest agricultural potential? So highest agricultural potential will be in the flat land or lowest slope, right? And you remember in class 1 we consider that it is near to 1% slope, and hence class 1 will be best suited for agricultural potential. So the correct answer will be A. Okay, so the next question is, in the land capability classification, class 8 typically indicates any answer for this? So capability classification we have seen, it starts from 1 and goes till 8, right? This is suitable for cultivation, and as you move towards the class 8, what happens? It is unsuitable for cultivation. But we have seen that there are some other use like slopes increase this side. So class 8 moderately good cultivation land, obviously not, because 8 is the last class that we have, so it is not suitable for cultivation. And slope is more than 25% steepest slope. Suitable only for wildlife, correct? So for 8, it is suitable only for wildlife, we have seen. Well suited for grazing and forestry, it will be less than, it will be less than the class 8, that is class 6 or 5, 6. Those are well suited for grazing and forestry. And gold cultivation land is in the earlier classes, that is 1, 2, 3, and 4. Okay, so the correct answer is B. Next question is, how does the trap efficiency? Okay, so before that we'll see the reservoir sedimentation first. Then we'll come back here. Okay, so next is the reservoir sedimentation. Sedimentation means what? The process of settling of the sediment is called sedimentation. You know that, right? So we know that rivers, like if you consider Ganga rivers also, Ganga river. So it carries a lot amount of sediments in it. Okay, if you come to the like downstream section of the Ganga river, you will see a lot of sedimentation happening. So these kind of rivers will transport huge amount of sediments, and it will shape the feature like river banks, deltas, alluvial fans, braided rivers, lakes, and levees, and so on. Okay, so we know we do some construction of reservoir in some of the river sections, and this construction of the reservoir will impede the sediment flow downstream, causing sediment accumulation. Because let's say if some river is flowing something like this, okay, and you blocked this way by making a reservoir kind of, or you have increased the area of this. So what will happen because of this? There will be accumulation of sediment here, right? And hence it will have a sediment accumulation within the reservoir, right? So like every rivers will have varying sedimentation rates. So all reservoirs eventually lose water storage capacity as the sediment occupies the water storage space. So let's say if you just see the, this one was the top section or top, let's say, and if you see this cross section or something, then what you can see, river is flowing in this direction, right? Like this. Okay, so this is the water level. So if you see the cross section, as it moves, what will happen here? Sediment will start forming. So here the space that was there we don't have now. So the flow will be only this much. Now if you go more downstream, it might be possible that the sediment is still here, something like that, right? Like it will be a slope, something like that, right? It will be something like this. So what it will create? It will create, or it will have a situation in which the water storage capacity will be less because sediment will occupy those water storage space, right? So this is the water storage space, correct? So like we have seen this, what is the dead zone in the um, dams and all we have seen, right? That's what is storage zoning, dead storage, right? So all those things. So what this reservoir sedimentation will do? The life of the reservoir will reduce, right? Because the water storage capacity will reduce, and hence the storage life or the life of the reservoir decrease, right? Storage capacity of the reservoir will decrease, okay, and hence let's say whatever for whatever purpose it was made, maybe for hydroelectric purpose it is made, it will be, the ability will decrease. Okay, for any other purpose, let's say if it is a irrigation reservoir, the irrigation ability will decrease. Okay, it will like reduce availability of water for irrigation. Okay. So mostly these sediments will be in the form of bed load, then suspended load, and wash load. So based on some of the classification lists, so let's say if you do the classification based on the prominent mode of transport, it will be suspended load and bed load. But if you let's say classify the sediment based on the particle size, it will be wash load and bed material load, let's say. So based on what kind of classification, based on which what criteria want to classify this sedimentation, there will be different kind of classification. Okay. So what is this bed load? Bed load means the material that moves along the bottom of the channel by saltation or rolling as a result of shear stress created by vertical velocity gradients in the stream flow. Okay, so let's say the river bed is there and the flow is happening. What will happen due to the stress? The shear stress will cause on the bed load, right? Because of the moving stream flow, and hence because of that, it will take the um, materials which are present on the bed, river beds, right? And because of which bed load will be created. What is suspended load? Suspended load means the material load that becomes suspended by the action of turbulence. And now see, the rivers or whatever section you consider, the water is flowing in the rivers, and hence because of this flowing water, there will be several materials or let's say whatever sediment, it will get suspended into the, or it will get mixed up into the rivers. Because of the flow, it can't settle. So if you just keep a normal water, then only it will sediment, right? Because if it is steady, so because of this moving water, there will be suspended load, right? Next is wash load. Wash load means what? The fine material that is carried by the flow in suspension but is not represented in the bed material. So let's say if some material which are coming from any other sources other than the bed material, okay, and that fine material is carried in the flow in the form of suspension. we consider that as the wash load. Okay, so for understanding like uh, for a reservoir, we calculate the trap efficiency. So what do you mean by trap efficiency of a reservoir? This means like how efficient it is to trap the sediments, okay, to block the sediments. So this doesn't mean that high trap efficiency means it is highly trapped. Okay, this means that the reservoir is more efficient to trap the sediment and hence it is better. Okay, so higher trap efficiency means better kind of situation. So when a natural water and the sediment flow is disturbed by creating a dam or reservoir, part of the water as well as the sediments are trapped in the reservoir. We know that. So let's say if water is flowing, we have created a dam and this is the downstream section, let's say. Okay, now because of this obstruction, what will happen? The natural water and the sediment flow is disturbed, right? Because we have blocked the part of the water and hence there will be sediments here forming here, right? So here the sediments gets trapped. So the trap efficiency of a reservoir is the ratio of total sediments retained by the reservoir to the total sediments entering into the reservoir. So see, the numerator is what? The total sediment that is retained by the reservoir, and the denominator is the total sediments entering into the reservoir. So let's say if I say let's say 5 kg of sediment is entering, okay, but only 1 kg is retained here. This means what? The trap efficiency is 1/5. Whereas if let's say here 2 kg of sediment is there, then 2/5 would be the trap efficiency, and hence the trap efficiency is more here, and hence there will be more trap. Okay, so it depends like how do you define the trap efficiency. So in some of the papers you'll see the definition will be like reverse of this. So based on that, like how do you define the trap efficiency? Based on that, you should understand that whether it is like reservoir sedimentation will depend upon this trap efficiency, which decides the amount of sediments deposited within the reservoir. Okay, so there will be several factors that influence the trap efficiency, like how much is the retention time of the runoff and sediment particles, what are the settling velocity of the sediment particles. So if it is like the size of the sediments is big, then what will happen? If the flow is not as much to retain that, the it will have settling velocity more than that of the river flow, and hence there, it will settle down as sediment particle. So there will be several dam characteristics also and so on. So how do you estimate this trap efficiency? There are several empirical estimation methods. Okay, some of these are Brown's curve, then Brown's curve, then Churchill method or Churchill curve. Let's say. Okay, so in Brown's curve there is one equation or the plot in which you use to calculate the trap efficiency. Okay, for Churchill curve you require one index called sediment index. Okay, we'll discuss this next time. So let's say for Churchill curve, there will be sorry, another. So there will be some curve like this. Okay, and it will be something like this. So this will be the Churchill curve, and it will be the plot between trap efficiency. Obviously, trap efficiency will be in either fractions or in percentage if you multiply by 100, right? or you can like it is in it can be in percentage if you multiply by 100 or in fractions, and here it would be sediment index. Okay. Okay, so based on this, how do you define this sedimentation index? Si will be equals to c by I whole square divided by L. Okay, here c is what? C is the capacity of the reservoir. Okay, at mean operating level. So capacity means what? It will be in volume units, that is meter cube. Okay, what is I? I is the average daily inflow rate, like how much inflow rate it has in meter cube per second. So if you divide the C by I, what will be the unit? It will be in seconds, right? How do you calculate the capacity? If you know the area and if you know the length, you can just, or the width, you can just multiply that and you get the C. Okay. And I, how do you get? I said is the inflow rate. So you can just calculate the volume and you can just, sorry, you can calculate the velocity. This is the velocity into area, right? This is the area, this is the length of the reservoir. Okay, and from there you can calculate the, and L is what? L is the reservoir length in meter. This is also at mean operating level. So whatever we are talking, it will be at mean operating level. So with using this SI, we calculate the E reservoir. What is E reservoir? This is the reservoir trap efficiency which we are looking for. Okay. How do you equations will be minus 20 plus, as I said, it will be a empirical equation 0.63 divided by 7500 plus inside to the power 0.63. So you will use, so there are several, you will use this when SI is greater than 6 into 10 to the power 4. Okay, if SI is less than or equals to 2.6 into 10 to the power 4, then what you use? You use this as minus 1.1 plus 0.25 into log SI. Okay, and if it is, let's say, SI is between or greater than that of 2.5 into the power 8, like a large value, you consider the trap efficiency as 1, because the capacity, the sedimentation index value is much higher. Okay, so like this you can calculate the reservoir trap efficiency using the Churchill curve. Similarly, you have the Bruns curve, which also gives some equation, empirical equation. E reservoir, that is the trap efficiency, will be equals to 0.000085 plus V by VW to the power 1.1 divided by, just if it is comes in the examination, yes, 1 for V by VW is greater than 0.003. So V is the storage volume of the reservoir below lying through bed level at the upstream boundary, and VW is the average annual inflow volume. Okay, so we'll go to the question. Okay. Next question is, how does the trap efficiency relate to the sedimentation in reservoirs? Can anyone guess or tell me what will be the correct answer? So the correct answer will be that trap efficiency helps mitigate sedimentation by capturing sediment particles, right? Okay, so the next question is related to calculating the trap efficiency using the Churchill method. Okay, so in Churchill method, how we start? Okay, you just read this once. Reservoir has the following dimension, that is L. L is what? L is the reservoir length. L is equals to 25,000 meter. Mean depth is 20 meter. Okay, and the mean width is 300 meter. Fine. The river just upstream of the reservoir has a depth h naught is 5 meter and width as 100 meter. Okay, so this is the dimension for the river just upstream of the reservoir. Okay, and the discharge or the inflow rate is 500 meter cube per second. The settling velocity of the sediment is 0.1 millimeter per second. The chase's roughness coefficient is 65 root m or root meter plus 7 per second. So we need to calculate the trap efficiency. Okay, I'll give 1 minute or 2 minutes to start, and then I'll also do. Okay, so in Churchill method, the first thing that we need to calculate is the sedimentation index, right? So how do you calculate the sedimentation index? That is C by I2 square by L, right? So L we have, L is 25,000 meter, correct? C is the capacity, and how will we calculate the capacity? Capacity C equals to, C is the volume, will be total area into the mean width, correct? So the total area is how much? Length we have this, mean depth is this. So on an average it will be like 25,000 into 20, which is the mean depth, right? So this is the L, this is the depth, let's say D, and width is how much? 300 meter, right? So just multiply this. So it will be around 1.5 10 to the power 8 meter cube, right? Now C we have, and I is how much? The inflow rate or the average inflow rate is, I is given as 500 meter cube per second, correct? So just put this here. C is 1.5 into 10 to the power 8 divided by 500 whole square divided by L is 25,000, right? Just calculate this. Okay, I am getting somewhere near 3.6 into 10 to the power 6. Hope you guys are getting the same answer. Now you see this value, if you have seen the equation, this is 3.6 into 10 to the power 6, right? And which formula we have to use will based on this. So SI here is 3.6 into 10 to the power 6. So it is greater than the first one, right? 6 into 10 to the power 4, and hence the first equation will be used, that is minus 20 plus 0.95. So we'll do that. So trap efficiency, V reservoir is equals to minus 20 plus 0.25 into SI to the power 0.63 divided by 7,500 plus SI over 0.63, right? So just put the SI value and tell me how much you're getting, and also check. Yeah, I mean, so I'm getting somewhere near 0.61. So the correct answer is B, 0.61. You guys got the same answer. Anyone? Any questions, any doubt here, or any steps that you didn't understand? Okay, if not, we'll move to the next question. So the next question, okay, next question is same, just we have to use the Bruns method to calculate the trap efficiency, right? So in this method, what we need the storage volume of the reservoir and the average annual flow volume, right? So storage volume of reservoir would be how much? Storage volume of reservoir below line, right? So we will say as L, that is 25,000 into mean depth is 20 into 300. So this one will be the, so the capacity we consider here as the storage volume of the reservoir. We write it as this. So how much we were getting? 1.5 into 10 to 8 meter cube, right? And other thing that we need in this method is average annual flow volume. Right? So VW will be equals to, so discharge is how much? So I have written there, right? And how do you calculate the inflow value? I is equals to velocity into area. Right, now you need this, sorry, you need the inflow volume, sorry. Right? So inflow value you calculate as 500 into the total time that it had taken. So it is for, will be for 1 year, right? So it will be 365 into, because it is annual inflow, right? So 365 into 24 into 24 hours, 3600 seconds, because this is in meter cube per second, right? How much we are getting in this? Can calculate and tell me how much you are getting. I am getting somewhere in here 1.57 into 10 by 10 meter cube. Okay, so the trap efficiency reservoir will be equals to 0.0005 plus V by VW 2 by 1.1 divided by 0.05 plus V by VW to the power 1.1. Right, just put the value and tell me how much you are getting. I'm getting somewhere near 0.42. Okay, so the correct answer is B, that is 0.42. Okay, this was simple. Any questions here? Right? Okay. Okay, so with this, like we are done with almost all the concepts in here in the topic that is covered in this course. Right. So now we'll move to some of the summary questions. Now before that, let us just summarize what all topics we have covered. What all topics we have covered? So we have seen what is watershed, what is hydrology, right? Then we move to what is hydrological cycle, what are its components, cycle and components. The components we have seen what are the hydrological cycle components like precipitation, evapotranspiration, abstraction, storage chain, runoffs. So all those, right? So then we started with each of the components like precipitation. We have talked then rainfall, like what is precipitation, how we can measure that. Right. Then we have seen the rainfall data analysis, like using the rainfall data, how we can analyze that data to get some information, right? Then we have data frequency analysis also, isn't it? Then we have seen other hydrological components like hydrological abstractions, such as like depression ponds, and then other abstractions like evaporation or evapotranspiration. Other than what all we have studied, like what is evapotranspiration, how you can like calculate or how you can estimate the evapotranspiration using like bicycle and so on. We have seen all this, right? Then we have talked about like what is infiltration, how you can estimate that, what are the methods, right? Then we talked about the stream flow processes and measurements. Then we talked about the flow duration curve, flow mass curve. Then we started with the runoff, like what is runoff, the introduction to it, the estimation. We have talked about the important concept for the SCS log number method, right? Then the most important was the hydrograph. We have talked about unit hydrograph, synthetic unit hydrograph, instantaneous unit hydrograph, and so on. Okay. Then we have also talked about the watershed characteristics, how it impacts and how its change impact, right? Then geomorphology of watershed, morphometric analysis also we have studied using remote sensing GIS. Then we have talked about watershed management through one like in like full week watershed management we have talked. Right, then we talked about hydrological models. In hydrological models, we talked about the like what are models, why we need these hydrological model. We have talked about the introduction. Then we have talked about how we can set up the model. What are the classifications of the hydrological models, conceptual models, empirical models, then lambda models, distributed model, and so on. And after doing the model setup, we talked about the validation, which is a very important part, right? Calibration and validation. Then we have talked about like how we can assess these models, how we can evaluate this model. Then we have talked about the sensitivity analysis of each of the parameters. We talked about the equifinality problem and so on. Right, we have talked about the machine learning methods which are recently used in hydrology. Then we have talked about the most important application because after learning all these concepts, we will move to the application parts like floods, how we can design flood for some dams, how we can do the flood frequency analysis, flood control, how we can manage, or what are the mitigation strategies we can adapt to control the flood, right? Then floodplain zoning also we have learned. Then we have also learned about the routing processes and logical routing, hydraulic routing. Then we have talked about other application that is drought classification, how we can manage the drought, right? And then today also we have talked so and so on. These are not the end of watershed hydrology, but most of the topics are being covered in this subject, right? Uh, so with this, we can apply all this knowledge anywhere. Okay, so with this, we'll do some problems that we might have done before, just to revise the concepts. Okay. So the first question is in the rational method of runoff prediction. Remember, we write QSCIA and all. Okay. So yeah. So in the rational method of runoff prediction, rainfall occurs at a uniform intensity for a duration of at least equal to dash of the watershed. Anyone might remember this? Anyone? So what was the assumption in the rational method? Rational method has the assumption of, here it is written, see, uniform intensity. So uniform distribution of the rainfall over the watershed for a duration equal to the time of concentration TC, right? So let's say if this is the basin, okay, something like this. So from the farthest or remotest location and the time that is taken to come to the outlet, we call that as the time of concentration, right? So the correct answer will be the time of concentration TC. Okay. Any question here? Okay. If not, move to the next question. So if a 4-hour unit hydrograph of a catchment has a peak ordinate of 60 meter cube per second, the peak ordinate of 8-hour unit hydrograph of the catchment will be, you know, so the here what you can see, the time or the duration of the unit hydrograph has been doubled, right? So what will happen to it? Any guesses? No one? Okay. So the correct answer will be less than 60 meter cube per second, right? Because if the duration is increasing and we have the unit hydrograph, that is for 1 unit of excess rainfall, then what will happen? The unit hydrograph value of, or the peak ordinate of the 8-hour unit hydrograph will be less than that of the peak ordinate of 4-hour unit hydrograph, correct? The correct answer will be 8, that is less than 60 meter cube per second. Okay. Next question is, using the binomial distribution, the probability that a storm with a return period of 20 years, so return period T is equals to 20 years, will occur once in 10 years. So N is equals to 10 years. And just calculate the probability. The success P will be equals to then what? 1 by T, that is 1 by 20 years, right? So just need to calculate the probability. Let's say X here, X is the event with return period 20 years, right? Might remember this from my distribution. Is it right? Are you right? You can write this as NCR P to the power R Q to the power N minus R. Right? If P is 1 by 20, Q will be equals to 1 minus 1 by 20, that is 19 by 20. Right? Just calculate this. N is how much? or NCR can be written as n factorial by r factorial into n minus r factorial into p to the power r into p to the power n minus r. Just put the values and get to it. I'll give 1 2 minutes for this. So it is like once in 10 years. So R is how much? R is 1. And N will be how much? 10. Just use this and do. Any answer you are getting will be 10 factorial by 1 factorial into 9 factorial into p is how much? 1 by 20 to the power 1 into 19 by 20 to the power how much was 9. Just calculate this. How much you are getting? Right? I'm getting somewhere near 0.3151. Right? So the correct answer would be D, that is 0.315. I hope you got the same answer. Okay, moving on to the next question. The next question is the most common chemical that is used for cloud seeding. We have seen that silver iodide, potassium iodide, or dry ice, like carbonate, we use that for generally for cloud seeding, but the most common is the silver iodide. Okay, so the correct answer is A. Next question is the infiltration capacity of a basin is described by Horton's equation, right? Horton's equation is I equals to 2 plus e to the power minus 3t, let's say, where I is in centimeter per hour and the duration t is in hours. Okay. Now, if the duration of the storm event is 2 hours, the depth of the infiltration in the last 1 hour of the storm event, and just calculate this after me. It's simple like this. So the depth, so see, the duration of the storm is total duration is 2 hours, and the depth of the infiltration in the last 1 hour you have to say. So last 1 hour means, so it's like 0 to 2 hours rainfall has happened, right? Rainfall duration, and last 1 hour means what? Last 1 hour means 1 hour to second hour. I mean first hour to the second hour you have to calculate. Okay, so this means what you have to calculate? You have to calculate integration first hour to second hour of this I to dt. That is integration 1 to 2. I is given as 2 plus e to the power minus 3t. Okay, dt. Just integrate this and get the answer. Simple, right? It will be 2t plus right, plus e to the power minus 3t by minus 3, right? Integrate this, sorry, values from 1 to 2. So I'll do it will be 4 plus width 1 minus 3 to the 6 divided by minus 3 minus 2 minus width 1 minus 3 by minus 3. Just calculate this and get the answer. Getting somewhere near 2.016 centimeter. So you have to give the answer in millimeter, because see I was in centimeter per hour, right? So that's why you got it in centimeter. Now you have to calculate in meter. Just multiply that with 10. Millimeter. So the correct answer is 20.16 millimeter. Okay, correct answer is C. Next question is, the dilution technique of the flow measurement depends on which principle? We know it considers the continuity equation, right? So the correct answer is the continuity equation. What does a distributed hydrological model consider in its simulation? It consider, so this aggregated catchment properties means only one catchment property for the not all one catchment property. So only one range of values of the catchment property for the whole catchment, right? So that is why we call that as aggregated catchment properties. So each of the catchment property for the whole catchment will be at the same value. That is what this. So this one is for lumped model. You know that. Uniform precipitation pattern. This also we consider for lumped model. Homogeneous soil characteristics for lumped model. But spatial variability we have. This is for the distributed model, right? So the correct answer will be D. Next question is, a soil conservation structure has an expected life of 10 years and is designed for a flood management of return period 50 years. The risk of this hydrological design percentages. I will take 1 minute and do that. So what is the return period? Return period T is equals to 50 years, right? And you need to calculate a soil conservation expected life of 10 years. So let's say expected life of n is equals to 10 years. You have to calculate the risk. So how do you calculate the risk? Risk will be equals to 1 minus q to the power n, where q is the failure. You know that, right? So q can be written as 1 minus q to the power n, that is, q can be written as 1 minus 1 by t to the power n. So that is 1 minus 1 by 50 to the power 10. Just calculate this in which you are getting. It is somewhere near 0.183. Okay, so the question was in percentage, so just multiply that by 100. That is 18.3%. Okay, so the correct answer is C, that is 18.3%. Next question is, calculate the NDVI for reflectance. We know NDVI is written as the reflectance value of NIR minus the red one divided by NIR plus the red one. Let's calculate that. Input is 0.65 minus 0.06 divided by 0.65 plus 0.06. Calculate this initial rating. So I am getting somewhere near 0.83. Now, correct answer will be B, it is 0.83. Sorry. Yeah, no, 0.83. Okay. Next question is, a catchment has a network of 4 rain gauges, right? The rainfall recorded by these rain gauges in a month is what, this much millimeter. The standard deviation, you know, to calculate the standard deviation, sigma n minus 1. How do you calculate? Root over summation pi minus p bar square divided by m minus 1, right? And p bar is what? P bar is the average rainfall. Average monthly rainfall. So let's try to calculate p bar, that is 40 plus 52 plus 54 plus 64 divided by 4. Let's calculate this. Initial rating 52.5 millimeter. Okay. So just put these values. So that will be equals to root over 50 minus 52.5 square divided by m is 4. M here is 4, right? 4 stations. So 4 minus 1 plus, I can write this as like this. So because anywhere the denominator is same, right? Plus 52 minus 52.5 square plus 54 minus 52.5 square plus 64 minus 52.5 whole square divided by 4 minus 1. Just calculate this. How much you are getting? Tell me. So I am getting somewhere here 9.849. So this is the standard deviation. Okay. So the correct answer would be B. That is 9.849. So yeah, okay. So this one would be option will be B. Okay. So the correct answer is B. Okay. So the next question is the main impact of agricultural drought is on. You remember the agricultural drought is mostly on the like soil moisture, how it affects the agriculture and crop yield. Yeah. So the main impact is on the reduction of crop yield. We have done this in last lessons, I think. Yeah. Okay. So correct answer is C. Next question is a unit hydrograph. A unit hydrograph is has one unit of peak discharge. No, it can have any value, right? One unit of time base of direct runoff, or one unit of rainfall duration, one unit of excess rainfall. So we have discussed in detail what is unit hydrograph and so on. So the correct answer is one unit of excess rainfall. Next question is the time of concentration of a catchment area is 26 hours, and the time to peak in hours for a 4-hour triangular shaped unit hydrograph is. Let's calculate this. It's simple, right? So for ACS, from the ACS triangular hydrograph, we know we can write TP is equals to D by 2 plus 0.6 into TC. Right? TC is what? TC is the time of concentration, and TP is the time to peak. So we need to find out the TP, and D is what? D is the duration of the rainfall. Okay, so just use this formula and get to that. 4 by 2 plus 0.6 into 26. 2 plus 15.6, that is 17.6 hours I am getting. So the correct answer is C, that is 17.6 hours. Okay, any question here? Okay, so with this we are done with today's assignment questions and all. We hope it will help you. So this one was the last tutorial sessions, as we know. I hope you guys have got good insights from these tutorial sessions, and all the best for your exam, whoever are writing the exam. Okay. Any questions? Any doubt? Oh yeah. That was just so. Okay. Thank you so much for this. Okay. We hope you are with it. So we'll move on now. Any questions? Okay. If not, we'll stop here. Okay. Thank you so much.